Okay, I hope everybody is back after lunch, and I hope you will stay awake.
Yeah, I always get the after lunch talks.
So yeah, so this is going to be, I suppose, probably the most interesting talk. So we are very happy to have Manju Sudhakar from Space Astronomy Group, URSC Bangalore, and she is actually involved with SOLEX and Helios both.
Yeah, we are X-ray
payload
yeah.
of Aditya-L1 mission. Yeah. So she will be talking about that, the science that you can do.
Thanks.
And later on, we will have a hands-on with these both payloads. So yeah.
Yes, thank you, Vaibhav. Okay, so hi everyone. So welcome to the post-lunch snooze fest, which I hope it won't be. So I would like to talk about the X-ray observations of solar flares by SOLEX and Helios and Aditya-L1. So all of you have heard of solar flares, right? So can somebody tell me what a solar flare could be? What is a solar flare? And I say solar flare, what do you imagine? Anybody? Burst of plasma. Okay, a burst of plasma. But do you actually see the plasma? You actually see the plasma? No, right? Do you see the plasma? So what part of the plasma do you see actually or observe during a flare? What is the property of the plasma that tells you that, there's a flare? Okay, so I'll tell you. So let's go back to the beginning there. So in 1859, scientist Richard Carrington, you can actually check out those papers, Emenra's papers, especially the first paper. It's extremely interesting the way he observed what is called as a solar flare. So what Carrington did is he projected the sun onto a projector kind of situation like this, where the diameter of the sun was around 12 inches. So 12 inches was 1-to-1 with the actual diameter of the sun. So what this guy was doing is he was interested in a gigantic sunspot region. So our previous speakers, Krishna and Vaibhav, they spoke about sunspots. So he was looking at sunspots. And as he was looking at the projected image of the sun, suddenly he saw brightness. And he thought that, okay, some scattered light is getting into my telescope. And he confirmed, no, it's not. It's actually changing with time. He became excited. He ran around trying to call somebody to see this phenomena on his projected disk. But when he came back, he saw that the intensity was starting to dim. And he clocked the time when he saw the brightness to the end to be around 5 minutes. So maybe around 17 hours after this brightening happened, telegraphs, in those days in 1859, you had the telegraph system. Okay, telegraphs all over the northern hemisphere, the higher latitudes, they started to catch fire. They burst into flames. They were short circuits. Papers caught fire. So in hindsight, this was called the Carrington event. And in hindsight, this phenomena basically demonstrated what is called as a cause and effect relationship between a phenomena on the sun to significant disturbances on the earth. Okay, and it initiated this whole slew of investigative efforts to understand what this phenomena is. So in 1892, Hale, you all heard about Hale, right? So Hale invented what is called a spectroheliograph. So what Hale did is that he used certain lines of ionized elements. So the previous speakers, all of them spoke about ionized atoms on the sun and how you can observe the sun in different wavelengths. So Hale was the guy who pioneered this phenomena, where he used the technology of the day to observe the sun in different lines. Say, for example, H alpha, and you have the calcium H and K lines, which the previous speakers, Krishna and Vaibhav, and of course, John Mayjoy also spoke about these images of the sun in different lines. So as you can see here, this is the first published photograph of a flare, which is taken using the calcium K line. So the left panel here shows you just before the flare has onset, and the right panel shows you when the flare has become maximum, what we call as maximum. So any of you remember which part of the sun can be observed at these wavelengths from your previous lectures? Do you guys remember? Which atmospheric layer of the sun is observed by these lines? Pardon? Chromosphere, excellent. So the first, apart from this white light, the other first photograph is taken about the chromospheric brightening on the sun during a flare. Okay. So what did the takeaway that Hale brought for us from this observation? That when you observe in a small wavelength, you can detect more number of flares than you detect in white light. Can somebody tell me why? White light flares are rare, could be rare. That are they rare or cannot we observe them? Is it the sensitivity of the observation is not good in white light? Can anybody tell me what could be the difference why white light flares are not, you don't get too many white light flares? Can anybody think about it? What is our sun? How do we observe our sun every day? Pardon? We observe our sun every day in what light? Visible light, right? So when you have a white light flare, how bright should the flare be so that we can see it against the visible disk? Right? It should be pretty bright. So even if there are teeny tiny flares that do show up in white light, they get lost in the brightness of the sun. So what Hale discovered using his spectroheliograph is that if you look in a specific wave band, you can detect flares. Okay, now the story becomes more of a history lesson right now. So you see these lists of dates that I've put here, and I've highlighted certain points here. Okay, so from 1926, so 1892, he discovered this, he invented the spectrograph. Then he invented a spectrohelioscope. So that is nothing but taking two slits, observing in a certain line, and scanning it across the disk of the sun. Okay, so you can actually capture dynamic phenomena as it's happening. And he mentioned when he observed a very large flare, it was the most remarkable phenomena he'd ever seen at that time in 1926. And then all the way down in 1934, we had this worldwide flare patrols. So flare patrols are not unique to this day and age. So nowadays we do have solar space weather kind of situations where we are monitoring the sun, trying to predict flares. But then way back in 1934, you did have these kind of flare patrols. Then I think Weber showed you that beautiful movie of a CME being erupted, observed by Parker Solar Probe, right? So how the prominence was ejected out. So again, they around 1937, they did find the ejection of prominence material with the associated with the flare. And it was visible to a height of almost 1 million kilometers. And it was followed by a fountain of prominences. Okay, so I'll talk to you about what this fountain type of phenomena was when I come to the X-ray part of solar flares. And then later they discovered the so-called double ribbon character of solar flares. And then a year later, they linked the connection between sunspot area and magnetic complexity with flares. And then in 1946, when just after the war got over, World War II, when they had these enhanced radars and radio instruments, they found that solar flares have radio emission linked with them. And then this was discovered later on that you had flare ribbons that are separated. And they found that these flare ribbons are adjacent to neutral lines. So based on this, the slide deck here, can we draw a picture of a solar flare based on what's written there? So they have something called, we have the disk of the sun, okay? And as our previous speaker spoke about, we have the chromosphere, right? Then we have the corona, the tenuous corona all the way there. So you have flare ribbons. Flare ribbons are ribbon-shaped brightness on the chromosphere that are mainly, that is first observed in H alpha. Okay. Then what did they say? They said they found radio emission. So radio emission comes from the movement of high energy electrons through plasma. Okay. So you must have heard about these plasma waves, right? So you have electrons producing these radio emissions. Okay. So, and then what did you have? You found these were linked with regions of magnetic complexity. You remember when Krishna spoke to you about the magnetogram on the sun's disk? You had white regions and black regions. So the white regions are magnetic fields that come out of the surface of the sun, and black regions are where the magnetic field lines go in the surface of the sun. Okay, so they linked brightening in the chromosphere. They found radio emission, which is due to electrons traveling through plasma and generating plasma waves. And then they found that these ribbons are linked with complex magnetic fields. Yeah.
Black markers.
Oh, it's not, sorry. Okay, thanks so much. Yeah. this is the white region, so the black region on the negative. Okay, so negative is field lines going in. And field lines going out. So when you say field lines going out and in, what do you mean? It means going out from the plane of the board and this is going into the plane of the board along the line side. Okay, so the flare, I've drawn a picture like this. Have I covered everything in this list? Can you see what I've drawn? There are ribbons. There are ribbons. Ribbons are, they look like ribbons. Okay, they can be straight. They can be curvy. They can be like this. They're called ribbons. Okay, then I have radio emission due to electrons, and then they're due to magnetic field complexity. So anything have I missed in this list? Do the ribbons move or are they stationary? There's something here called separation of flare ribbons with a speed of 1 to 10 kilometers. So that means that they discovered that these flare ribbons move apart. They separate as a function of time. The speed ranging from 1 kilometer per second to 10 kilometers. So something is happening in the solar atmosphere that is causing the chromosphere to brighten, the chromospheric brightening to separate, and streams of electrons being spewed into the corona, generating these radio waves. Something is happening. That is observed in all wavelengths. And I still haven't got to the X-ray part yet. Okay. So let's go to the concept of how Hale, again, he made a very great discovery about trying to understand how these magnetic fields are linked to sunspots. Okay. See, we take it for granted these days because everything is known. But in those days, Hale used the physics technology of the day, the experimental techniques of the day to try to understand how sunspots are linked with magnetic fields. So if you look here, this is what Hale did. This is a very nice, cute paper by Hale. It's a 33-page paper, and it is very nicely written. It's an AppJ, I guess, 1908. If you are interested, you can actually read it. It's very nice. Okay, so he's taken a slit, and he's made the observation as in a specific iron line, an ionized iron line. Okay, so the slit, when it's measuring outside the sunspot, you can find that the line is a single line here. But right within the sunspot, you find that the Zeeman effect has sort of split the line into three. Everybody knows the Zeeman effect, right? Can somebody quickly tell me what the Zeeman effect, why it happens, and what's the phenomenon? What do you get from measuring a line using the Zeeman effect? MSc students, have you studied that? Zeeman effect homework. Okay. Now, so using the Zeeman effect, Hale found out that sunspots have very strong magnetic fields. Does anybody know what the typical strength of the sunspot magnetic field is from previous lectures? Anybody remembers? Precisely, around thousands of Gauss. Okay, now that is in the photosphere. Now look at this figure here. This is a nice figure which shows you the different layers of the atmosphere. And you have the sunspots down here in the photosphere, which you cannot see. And you have the photospheric magnetic field that is shown there. Can you see photospheric magnetic field? So you find the white dot corresponding to your magnetic field lines going out of the plane of the field, and the black dots, black spots there. And as Vaibhav spoke about, as you go higher and higher into the atmosphere, you find that the magnetic field lines start to balloon out. What was the reason he told you in the morning? Yeah, scale height, yes. So you find that this is what is called as an active region. The active region is the manifestation of a certain sunspot group, a complex magnetic field phenomena in the photosphere, how it manifests itself in higher or upper layers of the sun's atmosphere. It looks so simple and calm on the photosphere. And as you go higher and higher and higher and higher, you find the complexity. And as John Majai said, the variation of the flux changes even within 12 seconds. Like for example, the AIA instrument on SDO, the atmospheric imaging assembly, you can take images every 12 seconds. If you take every 12 seconds, you can actually find out how dynamic the UV radiation is. Okay, so why am I showing you this? I'm showing you this so that I can talk to you about the fields as you look at different layers of the atmosphere. Okay, so let's look at the plot here, the left-hand side panel, and I have the lower plot or the upper plot. If you see, you can barely see there is a gray line there, and the right-hand side axis, y-axis, is the intensity. So the gray line talks about the intensity. Then you have the magenta or pink or whatever that color is. You have a line that is the magnetic field at the photosphere. Then in different layers of the atmosphere, you have different colors. So you have the chromosphere. Okay, in the lower, middle, and top chromosphere. So lower and middle and top chromosphere are nothing but the chromosphere closest to the photosphere and the chromosphere closest to the transition region. So they've divided the chromosphere into different layers and they've got the magnetic field, all of these are measurements. Okay. Then you look at the graph on the right-hand side lower part. That is a coronal magnetic field. So in addition to the pressure scale height, you do have the coronal magnetic field reducing as a function of distance away, which you have heard from the previous lectures as well. Okay. Now, I'll show you your favorite plot. You've seen this plot. This is the third or fourth time you're seeing this plot, right? Why are we also interested in this plot? Why are we so interested in this plot? Can somebody tell me? Why do people who are looking at different aspects of the sun, why are we so interested in this plot? Can someone tell me? Why is the plasma beta, which is the ratio of the gas pressure divided by the magnetic field pressures? You have the relationship there. You have it's proportional, beta is proportional to Ne by B square. Beta is inversely proportional to field. So you find that as you go out into the corona, what dominates? Which guy dominates in the corona? Pardon? And in the photosphere, it is the gas pressure. Okay. Now let's do a review of our favorite friend Maxwell. Okay, so you know these equations. You have Faraday's law and you have Ampere's law. And what do those equations tell you? It tells you that a changing electric field produces magnetic field, and a changing magnetic field or a gradient or a spatial gradient in magnetic field produces a current density. Okay, remember that very carefully. Okay, because we're gonna talk about something connected to Ampere's law soon. All right, and then you have Ohm's law. Ohm's law which it relates your velocity of the plasma, the magnetic field. Okay, and you have the electric field, and then you have your current density and your electric conductivity. Okay, so from here you get this fantastic term called the magnetic diffusivity. So when I talk about diffusion in very simple physical terms, what is diffusion? What is diffusion? Tell me. When you say something is diffusing, what does it mean? Pardon? Anybody? Little louder, guys. Little louder. Diffusion. When I say something is diffusing from one corner of the room to the other corner of the room, why does it diffuse? Yeah, there's a gradient. So remember, diffusion comes from gradients. So current density comes from gradients of fields. Diffusion happens when there is a gradient. Okay, remember those things. All right. Then when you combine these equations, you can actually derive the induction equation. Okay. So the induction equation, do you know how to derive the induction equation? Anybody has done this in your classes? It's nice, right? How to derive this? So can you tell me what the two terms are in the induction equation? You have the first term and the second term. Advection. So when you say advect, what does it mean? What does advection mean? Yeah. Yes. So there is a plasma velocity, and that is bringing the magnetic field with it. Is advecting the magnetic field with it. The second term is what is called as the diffusion term. Okay. So the induction equation is composed of two parts. You can either have the plasma dragging the field with it, or you can have the magnetic field diffusing. And the diffusion happens when you have a gradient, right? Okay, now if you take an order of magnitude, converting the nabla into an inverse length, you can get you can just approximate these two terms, and then you get the ratio of the advective term to the diffusive term gives you your magnetic Reynolds number, where magnetic Reynolds number is inversely proportional to 1 by diffusivity, and it is directly proportional to conductivity. Remember that. Okay. Now, so when you have a perfectly conducting plasma, okay, when your Reynolds number becomes infinity, your advective term will dominate. So you have what is called as ideal MHD, or the frozen flux MHD. Okay. So that means if I have, can you see this? The left-hand side panel is the photospheric image of sunspots, a complex sunspot region. And the right-hand panel is the corresponding magnetogram. So if you observe carefully on the top left corner of the image, this whole movie takes place over 4 or 5 days. So can you see, as the photospheric motions, photosphere is moving, the magnetic field that is on the right panel is also shearing, becoming more complex. So the photospheric motions are dragging the magnetic field with it. Okay, and so even though you have positive, negative, even though you have magnetic flux lines closely spaced in the photosphere, and you know that they balloon out, so any motion happening in the photosphere will reflect up in the corona as well. So you have whatever motions are happening here will be translated up above to the corona. Okay. Oops, sorry. So that's what these images tell you about. So if you look at the figure on the top left side, you have magnetic field polarities that can move this way, shearing. Okay. Then you can have them rotate. All right. And sometimes you have what is called as flux emergence. So you have a loop, magnetic loop sitting innocently there. And suddenly over time, you have a tiny loop that is already twisted, emerging from the surface, beneath the surface. So you can see that, especially if you look at the bottom right figure, can you see there's a gradient of magnetic fields there? Some of the fields are going this way, they're going that way. So what is happening there is you have what is called a current sheet being produced. So all of you remember, when there is a gradient in magnetic field, you will have a current density being produced, a very strong current density. That is your current sheet. Okay. And there are other ways in which this can also happen. Like, for example, the earlier speaker spoke about magnetic null points. What are magnetic null points? Does anybody know what magnetic null points are? Null points? Pardon me. So you have, that's also gradient, right? So you have a sudden change in the magnetic field direction, it is zero, it cancels out. So at that point, if there is a shearing motion, so let me draw that for you. So that is some. Okay. So if I draw, this is one polarity of magnetic field, the negative polarity, and this is the positive polarity. The null points are all along here. So as these guys move, this region is called what is called as the polarity inversion line. So this guy starts to get sheared. Okay. And one of the challenges that we have in observational solar physics is that we do not know how these magnetic null points are distributed in the very near or the low corona. It's still not known. People are modeling it, but if we do have some measurements of these null points, it will actually help in modeling these phenomena in a more knowledgeable manner, I should say. Okay. Now, what happens when you have when you have two oppositely directed magnetic fields coming closer and closer? You can shear the motion. What happens is that you have to use your imagination, guys. So when these things shear, how do the coronal field lines start to come closer and closer? So you find gradients of magnetic fields coming so close that the current sheet becomes so small that what happens? Diffusion of magnetic fields. They diffuse. They just diffuse. Okay. So that is where your ideal magnetic field, the frozen in MHD, breaks down. Ideal MHD breaks down in regions where you have a very strong gradient of magnetic field and the current density becomes so large, the current sheet becomes so narrow that field lines diffuse, magnetic topology changes. Okay, so this phenomena is called as magnetic reconnection. Okay, so you might have seen figures like this, right? Where you have a current sheets in the middle and you have magnetic field lines B1, B2. Across the gradient, you have the field lines diffusing across the current sheet region. And then you have what is called as plasma that goes in with the, so the plasma that is stuck with the magnetic field, it gets sucked into the diffusion region and they exchange lanes, if I can call it in a very colloquial manner. So when I talk to my students, sometimes I give them an example of the main road and the service road. You all know what the service road is, right? Sometimes on the highway, you have a service road. So if you imagine vehicles going this way on the service road, vehicles coming this way or this way itself. Okay, it's not the actual analogy of a magnetic field because magnetic fields are oppositely directed. But you imagine that vehicles on the service road cannot enter into the main road because there is no way for them to enter. And the guys on the main road cannot enter because there is no way. But once they find that point in the road, they can smoothly exchange. So imagine that point where the reconnection happens to be like a space in between the service road and the main road where plasma, aka vehicles, can actually exchange paths. Okay, it's a crude example, but it will help you remember. Okay, so look at the third figure, that is figure C. What happens is magnetic field lines, even though they are not a physical entity, they have tension, magnetic tension, you know that, right? So when this reconnection happens, the tension is also released and the field line suddenly shrinks. It shrinks up and it shrinks down. So when you have reconnection, you have what is called as post-reconnection loops. So post-reconnection loops, what happens is that when the reconnected loop starts, it snaps, it shrinks. This guy that is here, the one, the curved one that is there is a post-reconnection loop. Okay, then what happens is that the second line is there. After the curved loops, you have two more loops, right? Two more lines going up and down. Then it is their turn to get sucked into the diffusion region. So then they reconnect into that region, and you have a second reconnected loop. That is I'm sorry, this is not very good. So what happens is that you have a reconnected loop here. Okay, a reconnected loop here. Is this visible? This is where the reconnection region is. Then it's these guys' turn to correct. These guys will have to go in. Okay, when they finish reconnecting, they will appear here, the dashed line. Can you see? And the guys here will also start to go in, and they will reconnect here. Okay, so reconnection, post-reconnection loops will start to appear to be further apart, and they appear to grow. They don't appear to grow. It's only the further lines that are actually reconnecting and joining. If you can imagine that in your mind. Okay, I have a cartoon which is not very good, but I'll try. Okay, can you see? The colors might not be very good. So this blue U-shaped thing is what we can consider as a prominence. So prominences, according to what Krishna showed you, are basically suspended chromospheric plasma. They're suspended in the corona. They're heavy, they're dense, but they're supported by magnetic field lines. Okay, so those magnetic field lines are what you see here. These loops, right? You see those loops. Those are supporting this heavy, dense chromospheric plasma of the province. So when reconnection happens at those points, what happens? So in that current sheet region, okay, when the plasma gets sucked in, you have turbulences, you have shocks, you have DC fields, you have changing fields, you have all sorts of energetic processes happening within few nanoseconds or even microseconds happening within that small current sheet. Okay, so what happens to the ambient plasma and the corona? They get hot and they get accelerated. When I say hot, what do I mean? I mean that you know that yeah, so you know that the corona has a temperature of around 1 megakelvin, right? Okay, so when I say hot, I would assume that they follow a MB distribution, right? What does an MB distribution tell you? Yeah, so what does it tell you? What is the Maxwell Boltzmann? So what's on the x-axis? X-axis velocity. Yeah, there's only a probability. So most of the fellows are at a velocity that corresponds to 1 megakelvin. So inside that place where the reconnection happens, these guys get hot, almost at 10 megakelvin. So in the project work which you will do with SOLEX data, you look at the hot plasma that evolves during a flare. So from the ambient 1 megakelvin plasma, the corona, you can hit 10 megakelvin and 20 megakelvin sometimes. And you guys know about the RESI instrument. There was an instrument called RESI that was decommissioned maybe some 6 or 7 years ago. They had an imager. So using the imaging technology, they found out that flares can go up to 30 to 35 megakelvin. That's super hot flares. Okay. So in that small region, you get superheating. Okay. So what happens is that plasma does not remain at the same temperature all the time. You have pockets of plasma at different temperatures called multi-temperature plasma. So for example, the SOLEX instrument, okay, we look at plasma up to around 25 megakelvin. Okay. And the Helios instrument has another detector, which can also sample 25 megakelvin and up to around 30 to 35 megakelvin. Okay. For very, very hot flares. Okay. So when you look at the sun in different wavelength filters, we're actually sampling the plasma at different temperatures, which Weber showed you that table, you remember. Same way, in X-ray, you are going to sample the extreme ends of the temperature that plasma can get to during reconnection. Then acceleration. What is acceleration? So you see something called non-thermal particles. Can anybody tell me what non-thermal is? Thanks. What non-thermal is? Okay, so you see these non-thermal particles. So what is non-thermal? When I say non-thermal, what does it mean? This is thermal, right? What is non-thermal? Exactly. So in that region of reconnection, you have heating and something else that is making the particles come out of this thermal distribution. They're non-thermal particles. Okay. And pink shirt, maroon shirt, anything funny? You're okay? You're understanding this? Thank you. Okay. So you have particles that are accelerating out of this region up here, and they're accelerating down here. Okay. So what happens next is, can you see some of the particles, these magnetic field lines, they reconnect with these open flux lines. Can you see? So particles stream out and escape, and these escaping particles actually emit radio waves as they stream out into the plasma. All right. And some of the precipitating particles come down, they hit the dense chromosphere, and they heat up the plasma to such temperatures that the chromosphere becomes very bright. Those are your flare ribbons. Why they're called ribbons? Because if you have an arcade of loops. So this is called an arcade of loops. If you have an arcade of loops, all those loops brighten and they look like a ribbon. They appear to be like a ribbon. Okay. Now, what's happening here? Okay. Here what happens is, can you see these dashed lines here? These dashed lines are the reconnected magnetic fields. Okay. And after reconnection, these guys, can you see here? These guys, these curved ones, they are the post-reconnection loops. Okay. And can you see these contours here, white contours? That is actually X-rays emitted, which are both hot, and X-rays emitted due to the non-thermal particles. And can you see these green guys going down, the green, the particles here? These yellow contours are non-thermal X-ray emission. So X-rays from solar flares, the diagnostics, what is the diagnostics of the plasma that they can give you? They can talk about the multi-temperature plasma. They can also give you information about the non-thermal particles from the X-ray emission. Okay, so now I talked to you about this, right? After reconnection happens, you have a reconnected loop. When the next loop gets reconnected, you have the next reconnected loop, this dashed one, appearing to look higher, and the foot point appearing to move outward. Okay, so if I show you the X-ray image of that, so can you see this? This is the reconnected loop after one reconnection, meaning one set of lines reconnected. Then the next guy starts to, this is the cusp which Vaibhav spoke about, where plasma beta may not always be less than 1, right? So this is the cusp. The cusp is the point which talks about the tip of the post-reconnected loop. Okay, so reconnection, this part, right, is way too faint and it's already happened. But in X-rays, this part is very dense because the plasma is like a dense and hot plasma that is in this point here. Okay, now when you go further, you find that the loop appears to grow. It appears to grow because you're seeing the next reconnected loop. The other guys have all cooled down in the meanwhile, and they are too cool for us to see in X-rays, but you might see them in other bands. Okay, then when you go to the next, you find that it has appeared to grow a little bit more, and it appears to have spread. So in my slide about the historical perspective of solar flares, we spoke about flare ribbons appearing to move, separate from each other, right? So that appearance of motion or movement is only because of the phenomena that we're having, reconnecting lines continuously happening. Okay, now, so let's come to this very famous figure of solar flare intensity and time diagrams, or time profiles, or light curves in different wave bands. Okay, and depending upon which wavelength is observed at which time of the flare, we actually call them, we actually name them as different phases of the flare. Okay, so you saw that radio emission and high energy non-thermal emission occurs, and your H alpha ribbons, all of them happen at around the same time. They happen almost simultaneously. That is called the impulsive phase. The mic is.
Change the battery. Just use it for.
Sure.
No, use for bulb.
No problem. It's okay. I think I'll use this.
No problem.
It's okay. I'll use it. Hello, hello. Something is not. Oh, it's this one. This one? Yeah. Okay, sorry. You can hear me? Hello? No. I think my pocket is going. Hello? Yeah. I'll use it. Thank you. And I'm audible? No. Sorry.
Yes, now you must be audible.
I'm audible?
Yes.
Yeah. Okay, I think.
No. Just.
Oh, yeah.
It's fine.
I think so. Yeah. Hello. Yeah. Okay. So, yeah. So as you can see here, we have the time versus light curve. Okay, and you have what is called as the impulsive phase of the flare, which coincides with the H alpha brightening of the chromosphere, as well as a high energy non-thermal, I won't call it high energy, I'll call it non-thermal X-rays being emitted from the chromosphere, okay, as well as the radio. And then you find what is called as the decay phase, okay. So can you see which wavelengths are showing decay? And if you decay, what does it mean? It doesn't mean something actually decaying. It's basically the plasma, the hot plasma is cooling down. When it cools down, what happens? It loses its heat, or what do you call, the content of energy in the specific wavelengths, and it starts to come down in brightness. So when it stops coming down in brightness in one energy, one wavelength or energy regime, it picks up in another one. For example, if you see soft X-rays here, you find that soft X-rays peak at a certain time. Okay, but if you look at extreme ultraviolet, you find that it peaks after the soft X-rays. So that's because the plasma that is hot enough to emit soft X-rays has cooled down and starts to now emit radiation in EUV. And then in other wavelengths like UV and so on and so forth, until we cannot see those loops anymore. But that doesn't mean they're not hot. They're not hot enough to emit radiation in the wavelengths or energy bands that we're interested in. Okay. So then you have, I'm not going backwards and forwards, but you have what is called as the pre-flare phase. Okay. So the pre-flare phase, can you see here? It is not observed in the hard X-rays and the microwaves. Okay. So you might be wondering, I'm suddenly throwing terms like hard X-rays and soft X-rays. Okay. So yeah, I'll just change the name. Sorry. Okay. Okay. Yeah. So I talked about soft X-rays and hard X-rays. Suddenly I've thrown this term at you guys. So when you say something is soft and hard, what does it mean? It means that the energy, now we are changing our track from wavelengths, from angstrom, nanometers to suddenly to KeV. So when you talk about X-rays, they basically are tending more towards the particulate nature of light than the wave nature of light. So we are going from the wave nature to the particulate nature. So we talk in terms of energy or kiloelectron volts. Those are the units that we use here. Okay. So when I say soft X-rays, they are of lower energies. That is less than what is 25 keV. I'll come to those terms later on. And when I say hard X-rays, I talk about those with extremely high energies. Okay. So they can actually, what do I call it? It's like when you go to the dentist or when you go to a doctor for an X-ray. Those X-rays don't fall in the category of hard X-rays. They're very soft X-rays that can just penetrate your skin and muscles and reach and create a shadow of your bone. Hard X-rays will not even give you a shadow of your bone. It will pass right through your bone. So you can try to imagine or understand what soft X-ray and hard X-ray are from that. Okay. So what you see here is the different phases of the flare and the different wavelengths in which these phases are observed. Okay. So when I talk about X-ray emission from flares, we have to talk about what is called as Bremsstrahlung. How many of you have studied Bremsstrahlung in your courses? The figure is very self-explanatory. Somebody can simply give me an explanation. Anybody? What is Bremsstrahlung? This mic is not helping. So what do you see here in this figure? Can somebody describe the figure to me? Yeah, exactly. So is Bremsstrahlung continuous emission, or do you have lines from Bremsstrahlung? Why? What is the fundamental? Do you have any? Do you remember how you derived Bremsstrahlung? Is there any derivation that you've done? No. Anybody's done derivation of Bremsstrahlung? What are the parameters that are important when you talk about Bremsstrahlung? Impact parameter. So impact parameter, do they have one single impact parameter or can there be a range of impact parameters? Yeah, so when you have a range of impact parameters, you have a range of wavelengths or energies. So Bremsstrahlung emission is always a continuum. Okay. So depending upon how much it decelerates or accelerates, it will tell you what is the energy of the wavelength. So you have high frequency, which is your high energy Bremsstrahlung, which are, you can imagine them that will never create a shadow of your bone and an X-ray. And then you have soft X-rays, which or low energy and Bremsstrahlung, which will give you an X-ray when you take a picture of it, the picture of a tooth, for example. Okay. So if the distribution of plasma, what is this distribution? Okay, who else can tell you what this distribution is? Yeah. Okay, so this is the thermal distribution of plasma. So when the electrons are distributed in a Maxwell distribution and they emit Bremsstrahlung, it is called thermal Bremsstrahlung. Okay. So what is this distribution? What is this distribution? What are the parameters in this distribution compared to the previous one? Anything common? Anything not common? Okay, one more small question. In the thermal Maxwell-Boltzmann equation, apart from velocity, what is the most fundamental defining parameter there? What is it, apart from velocity, what is it? Pardon? Yeah, the second equation. Yeah, but energy is there in the first equation, you have velocity, mv squared. So what is the fundamental difference between the two? One doesn't have temperature, as we said, it's a non-thermal equation. That is what is called the non-thermal equation. You do not have any temperature dependence. So when the electron distribution has this format, which has no temperature dependence, and it emits Bremsstrahlung, it is called non-thermal Bremsstrahlung. Okay. Then, in addition to what is called as the free emission, you have what is called as a free bound emission. So the exciting thing about X-rays, observations of solar flares, in the soft X-ray regime or the low energy X-ray regime, you can have lines, emission lines. So the SOLEX data, you can actually look at the different elemental abundances of the hot flare plasma. For example, iron and calcium, right? Calcium and other stuff. And you can actually study how those elements vary as a function of the flare light curve. Okay. This is how it looks like. So Abhilash, I think, has simulated this. So he's taken different values of plasma temperature. Can you see this? 5 megakelvin, 10 megakelvin, 20 megakelvin, 30 megakelvin. And he's modeled how the flux would look like at different temperatures. Okay, so you can find that the energy, okay, the maximum energy at which the emission occurs increases with increasing temperature. Can you see that? And the content of or the flux also increases with temperature. And if we probably normalize these line intensities as well, we will find something interesting as a function of temperature as well. Say, for example, this line here is the iron nickel complex, right? Abhilash is an iron nickel complex. But if you look at the flux emitted at 5 megakelvin, you don't see that line. That's because the plasma is not hot enough to emit or ionize. I think it's iron with helium-like or hydrogen-like ion ionization. So when I say hydrogen-like ion ionization, what does it mean? It means that iron has 26 electrons. All the electrons but one are removed. So those temperatures are required to emit X-rays at those high energies. Okay. Now this is what is called as a non-thermal Bremsstrahlung spectrum. Okay. So let's
Feel free to try to understand what this is. If you recall the equation for you had electron distribution, non-thermal electron distribution, non-thermal, proportional to e to the power of some delta, right? Yes, times delta. Okay, so what Abhilash has simulated here is the index we got there is the index of the electrons, right? So he has assumed a power law with a low energy cutoff. So when I say low energy cutoff, what does it mean? It means the power law does not extend all the way up to the lowest of the low energies. Okay, there is a reason for that. Okay, so I think when I may touch upon this if I have some time. I'll go on ahead and then I'll cover that. Okay, so this break energy here is a very important concept, or the low energy cutoff energy, what they call it. Okay, so I've written here thick and thin. Okay, so the physics behind emission of non-thermal X-rays from the sun has a lot of assumptions. They assume that the atmospheric layer which emits these X-rays is a cold, thick target. So when I say cold, I don't mean 300 degrees Kelvin, no. I mean colder than the corona. It's cold. Okay, cold. Thick target, what does it mean? It means that there is a single density, there is no variation of density, and all the electrons lose their energy through collisions and they emit Raksha. And there is a thin target. The thin target emission happens, if you recall, when I showed you the loops, which has a kind of a X-ray emission on the top of the reconnected loop, we call those contours. So that is what is called a thin target. That means the electrons, as they move, they emit radiation. They don't lose their energy as they move along. Okay, so typically we have X-ray emission happening from the corona. We use a thin target model, and if we have X-ray emission coming from the chromosphere, we use the thick target model. That's basically what we use. Okay, so now we come to how solar flares are classified. Now you've all heard about M-class flares and X-class flares, and oh my goodness, an X10 flare occurred. CME has happened, then we have these solar storms and auroras, and we've heard all these things, right? So X and M and C and A and B, sorry, or B and A, are nothing but names given by NASA's aeronautical NOAA. I forgot. Okay, so NASA's space weather astro thing, they actually named these flares based on the flux observed by the X-ray spectrometer on the GOES satellites. Have you all heard of the GOES satellites? Right? Yeah. So the GOES satellites have two channels. Okay. One channel, if you can see here, the blue and the yellow. The blue one measures 1 to 8 angstrom. So if you plug that into the equation that is below, you can compute what is the energy range. That is 1.5 keV to 12.5 keV. And then you have the 0.5 to 4 angstrom, which is a shorter wavelength, but you get a higher energy range. And the SOLEX instrument on Aditya-L1 covers both the GOES ranges. Okay, but the GOES instrument gives you only the light curve or the time history. That is the time versus the flux. Okay. What SOLEX gives you is that it doesn't give you broadband light curves, it gives you a spectrum, and we'll come to that soon. Okay. So now when you define solar flares, now we can define solar flares from our historical observations and everything we discussed so far. We can define solar flares to involve the rapid acceleration of coronal electrons. Does it make sense? Does it make sense with everything we discussed? To relativistic energies, along with the radiative emission of a broad variety of spectral signatures ranging all the way from X-rays and gamma rays to radio emission. So all the observations we made since 1859 all the way to now, we are now able to define what a solar flare is, right? It's a sudden brightening across all wavelengths. Okay. Now, you know what this is. We've come here for this, right? Aditya. So the movie there shows you Aditya's journey, Aditya-L1's journey from the Earth all the way to the L1 point. There it goes. See how long it takes? Okay, there it goes. Yeah, not the full halo orbit. Okay, so it was inserted into the halo orbit on which day? Anybody remember? We had a big function this year to commemorate that. The people who went for the function don't say it, but does anybody know when Aditya-L1 was inserted into orbit, halo orbit? Yes, very good. 6th January. That was the day when it was inserted into the orbit. Okay. Now, this is the Aditya spacecraft. Okay. So you see, you have all the different instruments. Today, John Midrai spoke about SOOT. SOOT is way up there. Can you see? Yeah, that's SOOT. Okay. And Weber spoke about coronal mass ejections, CMEs. That's BLC right here. Okay. And SOLEX is sitting right below SOOT. So SOOT is this green instrument here, and SOLEX is sitting right behind. Okay. And can you see this mysterious keyhole here? Yeah, that's where Helios sits. So SOLEX sits here, and Helios is sitting inside this keyhole. If I make this part transparent, you can find there's a cutout here, and Helios is peeping out from there. So Helios is sitting inside the spacecraft, and SOLEX sits outside, and this is the detector, SOLEX, the instrument here. So SOLEX has two detectors. One detector is mainly for measuring very strong flares during the solar maximum. What is solar maximum? You've heard about it today. What happens in solar maximum? Yeah, so magnetic solar activity is very high. So SOLEX has one detector to detect flares during high solar activity. So we have all the strong flares. And then they have another detector that can be used to detect tiny flares, like micro flares and nano flares when the solar activity comes down. Okay. Now, Helios has two detectors. Okay. It basically has it has one detector that acts as an overlap between two other detectors. One detector from SOLEX, and there's another high energy detector in Helios, which is the cadmium zinc telluride detector. I'll talk about that soon. And then we have what's called the cadmium telluride detector. So we can cover a broad band. If you use all the data from SOLEX and Helios, you can cover from 1 kiloelectron volt all the way down to 150 kiloelectron volts. So a huge broad band. Okay. Now, here are the instruments. If you want to talk about these instruments later, we can talk later. I don't want to spend much time on this. What I'd like to point out to you is, you see this big black box here? That's where the electronics of SOLEX instruments sits, all the electronic cards, the cards that process the data from the detectors, the cards that packet the data and send it to the spacecraft. And in this contraption here sits the detectors. The detectors are facing that side there, Abhilash, that side, yeah. And this is a Helios instrument here. And you see this big chunky thing here? That is a collimator. So for Helios, we have what is called as a stainless steel collimator to restrict the field of view, to make sure that we get the sun in the field of view and we don't have too much over the sky as well. Okay. And the detectors sit in this, can you see? Why is it changing? Okay. Yeah, I thought I did something. Okay. So this box here, right? Can you see this box? You can barely see the cursor moving this way. Can you see? In this tray, behind the collimator sits the detectors of Helios. Okay. Now, these are something which we instrument people really like to make. This is called an instrument specifications table. Every single review, every reviewer wants to see an instrumentation specifications table. So what does this instrumentation specification table talk about? It talks about the energy range of the instruments. It talks about the kind of detectors that you're using. It talks about the number of detectors you're using. And it talks about something called the spectral parameters. So what is the meaning of resolution? When I say resolution, what does it mean? Anybody? In any context, what is resolution? Yeah, exactly. So when I say energy resolution, it tells you how well you can separate out different energies. So that is a very critical thing that is required for all spectroscopy instruments. Okay. And then you have what is called the geometric area. So the geometric area tells us how many photons or how much of flux an instrument can detect. Okay. Now, SOLEX has an energy range of around 1 to 22 keV, which is overlapping with GOES, right? And Helios has an energy range of 10 to 150 keV, right? Everybody okay with that? However, look at the size of the detectors. Okay, you have something called a small aperture detector, which I told you will look at very strong solar flares. Then you have another detector that will look at the square sun, the nano flares and the micro flares. Okay, and I can understand when you want intense flares, you need a small area. When you have very dull, dim flares, a large area is quite good. But when I have a high energy, why am I going to high areas? So this is 50 millimeters square. This is 32 centimeters square. The CZT or the cadmium zinc telluride measures X-rays from around 35 kV or 20 kV up to 150 kV, the highest run. Why do those detectors need a larger area? I'll give you some clues. They all detect non-thermal Bremsstrahlung, which is a continuum. Okay. And so if you look at the spectrum of Bremsstrahlung, you remember what it looked like? This was energy in kV. It looks something like this, right? So the higher in energy you go, the lower is the flux. So to capture higher energies, which have lower flux, you need larger area. So in the most beautiful thing about high energy physics is that the more energetic the process, the more deficient you are in photons. Because it takes a lot of energy to accelerate the plasma to make it radiate such high energies. And there are some poor souls who work in TeV gamma ray astronomy. And if they get one photon in 1 year, it's a big deal for them. So the higher energy you go, the less photons you get. Okay. So that's why we need a higher energy detector for high energy X-rays. Yeah.
This video view is at the sun, or I mean, it's half an inch, right?
Yeah.
So if you increase it, it shouldn't matter.
It shouldn't matter for us, it shouldn't matter. Yeah.
So
But,
how
oh, you mean to say for the SOLEX one, right?
Yeah.
Yeah. We should have.
It's the aperture. So it's determined by the aperture. So area we are that is the instrument. The video view 1.8 is that the instrument, or can you go back to the image?
Yeah.
Yeah.
Sorry. Yeah.
So detectors are sitting at the back, and the apertures are in the front. There is around 150 mm of gap. So two apertures, one is pointed back, one is straight.
I think here you can see it, right? This one.
No, so this is the back.
Back, that's the front, right? Yeah.
So, so the angle is determined by your aperture area and size of your. So, we are selecting the aperture area, which determines what is the flux level you get at the different. But essentially, that is telling the angle at the detector, right? It's not telling the angle at the sun. No.
Yeah,
It's the field of view found it. So, sun is in the field of view sun. Oh.
Yeah. So it's just like you're subtending the sun at your detector. So in the case of SOLEX, it is pretty much constrained around the sun's actual size. But Helios is all over the place, like 6 degree west. So wherever in that, if only the sun comes, it doesn't matter for us. But first, what we need to do is we ideally should have a very constrained field of view. But the collimator will become pretty long in that case, and we're already pretty heavy at 8.2 or 9 kgs. We didn't want to do that. We have to optimize up to what energy we can stop, extraneous X-rays from contaminating. So that was a optimization method calculation we had to do. So that was a big method. Thanks, Abhilash. Yeah. So now we're going to jump into some instrumentation, applied science, engineering, what you call it. Okay, because to understand X-ray interactions and analyzing the data, fixing the spectra, you have to know how the detector actually detects X-rays. Okay, so very simply, if I say consider the detector to be like a capacitor, whether it is silicon, whether it is cadmium telluride or cadmium zinc telluride. So cadmium zinc telluride is nothing but an alloy of cadmium telluride and zinc telluride. Okay. So when you add zinc to cadmium telluride, you can actually play with the band gap. So what is band gap? All of you say about PN junctions, band gaps. Anybody know me? Pardon? I don't. Yeah. So what is the big deal about that? Why do you have to increase the band between conduction band and valence band? Because when I put zinc into the cadmium telluride, I'm increasing the band. Yeah. So why is it important to increase band mass? When you don't have somebody said something about band gaps and have you heard about reverse bias, forward bias? Okay, reverse bias. Forward bias. What happens in forward bias? When you put P and N type semiconductors together, what happens? Anybody can tell? I think you are nodding your head, right? P and junction. Yeah. Forward bias. Yeah. So what happens in that case? What is the forward bias junction used for? Okay. So in reverse bias, what happens? You connect the other way around, right? So what happens to all the any charge carrier, electron hole pairs? Have you heard of? So when something happens, when you heat, when it's ambient room temperature, you have electron hole pairs being generated by thermal heat. So in your reverse bias detector, what happens to the thermally generated electron hole pairs? Pardon? Yeah, they're what? Some of the people become who's it? And the reverse bias, what happens? Okay, that is true. But you have thermally generated electron hole pairs inside that junction. And you reverse bias. Suppose I have reverse bias, she said forward bias, she said some polarity. Reverse bias is the other way around. So what happens? When I have thermally generated electron holes, right? So what happens to the thermally generated electron hole pairs? You reverse bias. Pardon? Yeah. So electrons are circulating, the holes are circulating. So in a reverse bias condition, you have absolutely no free charge. Every single free charge is swept away by the corresponding electrodes by virtue of how it is connected. Okay. So you have no free charges. So detectors, silicon, CVT or CGT are all reverse bias diodes. Okay. So when an X-ray is incident on this detector in the reverse bias condition, I'll explain to you how this happens in the next slide. So imagine an X-ray comes, you have electron hole pairs being created. Okay, they're swept by the reverse bias contact, and that is how we detect an X-ray. Okay, now in SOLEX, for example, we use what is called as a silicon drift detector. So in a silicon drift detector, instead of planar anode, you have an anode which is angular. Okay, and the voltage is applied at the centralmost point. So all the charges are collected in an angular radial fashion, and which allows the charges to be collected very quickly. Okay, I hope I'm not flying over all of your heads. Are you all okay? Are you able to understand so far? Am I boring? This topic might be a little dry. Okay, I am sorry, it is a little dry. Okay, so anyway, so what I'll do is I'll try to show you this flow chart. Okay, so consider we have an X-ray energy, E epsilon something. Okay, that is incident on your detector. Okay, now what happens? You can get a certain number of electron hole pairs. So how do you get the electron hole pairs? Electron hole pairs is equal to, or the most or an average value of electron hole pairs is equal to the energy of the incident X-ray divided by what is called as a work function. You know a work function, right? It is the minimum energy required to produce an electron hole pair in equity. So silicon has some number, cadmium telluride has some number. Okay. So then if you can get a total amount of charge Q. So one X-ray with an energy E will give you a number of electron volt pairs determined by that equation, and that will amount to a certain amount of charge. Okay. Next step. Oops. Yeah. Now you have to bias it, right? Apply a voltage B across the depletion depth L, and you can get an electric field. So the electron hole pairs are swept away by the electric field. Okay. Oops, I jumped. So then what happens is that you get an induced current. So when charges move, they induce a current on the electrodes. Okay. So the charge that induced current is given by. Does this equation make sense? Induced current by the total number of charge given by this. Okay, it makes sense, right? Okay, let's carry on. So let us call this. Let us consider this signal current to be the input to what is called as a charge-sensitive preamplifier. You all heard of amplifiers, right? What do amplifiers do? Yeah, exactly. So before they go to the amplifier, X-ray signals, extremely high energy charge particle signals, gamma ray signals have to all be preconditioned. Because if you actually put the value of some energy E here and calculate the total amount of charge, you'll find it's really, really small. So you have to precondition that charge, that signal, before you take it to the amplifier. So you take it to what is called as a preamplifier. So the preamplifier has a certain amount of gain. That gain will cause will convert this charge or current pulse into a voltage pulse. Okay, so the voltage pulse will look like this. Observe this part. Okay? This is the time. This is the voltage. It will look like this: a fast rise and a very long tail of the order of few 50 to 100 microseconds. After the signal goes to the preamplifier. Okay. So then what happens is you take it to a shaping amplifier. You have differentiators and integrators that does low pass filtering and high pass filtering. All of you learned that, and you get what is a you get a pulse. You see that? So this red trace that you see here is the signal that comes out of the preamplifier, and after taking it through the shaping amplifier, you get a very beautifully shaped, filtered, Gaussian-like pulse. Okay. Yeah. Okay. Okay. So then what you do is that these voltage amplitudes that you see here are digitized. So every voltage that you get is given a digital number, which we call as a channel. Okay. And oops. And then when you make a histogram of all those channels, you get what is a distribution like this. So a single energy E becomes a distribution of channels. So there's something very critical happening here. There's no one-to-one relationship between the incident energy and the energy that you're actually measuring as an output of a detector. A single energy gives you a spectrum of digitized numbers. Okay. So what this is called is an instrument response function. You will be encountering this when you look at the SOLEX data analysis. The guys who are looking at in that project, you will have to look at understand the response, and I think Abhilash has a good notebook which will demo it for you. Okay. So for every known energy value, if you have in your laboratory some known values of energy, okay, I know the values of the incident energies. I can get what is called as a calibrated energy spectrum. Okay, so when you make an instrument, it doesn't matter that you are going to discover some very great science. If your instrument is not calibrated, you cannot make any sense out of the data that you got. And the best of ground calibrations will never be the best. Because when you go to space, it's not the same conditions as on the ground. So calibrating an instrument is and understanding the response. Because some strange feature that you might not have encountered in the lab, you may encounter in space. You have to make sure that at every temperature, at every energy that you have in the lab, you should calibrate your detectors. Okay.
So you
Yeah.
just
Sorry.
correlate this response function that I showed for you. So this channel corresponds to your energy.
Energy, yeah.
Because here that
Yeah, that's right. Okay, so these are some screenshots of cable. They are not, are they clear?
Oh yeah.
Sort of. Okay, so this is to show you how the spectral response function of the instrument like Helios looks like. Okay, so as Vaibhav pointed out, here what you have here, these values that you see here correspond to the energies that your instrument is sensitive to. Okay, and for every incident energy, I have a corresponding response or distribution of that energy among all the channels. Is that okay? So for every energy, you must generate this. So you have a matrix. A matrix, the rows of the matrix are your incident energies, and the columns of your matrix are the channels or the engineering units in which those energies are distributed. That is your instrument response matrix. Okay. Then there is something else called the detector efficiency. So you spoke about resolution. The resolution is the ability to resolve through well-spaced, closely spaced lines. So you see here, this is a spectra in CTTE and silicon. Okay, so silicon is the material used in the SOLEX detector. Okay, so as you see here, the same energy, that is around 6.5. The silicon detector is well able to resolve the two lines, whereas the CTT is not able to resolve it. It is resolvable, but not by much. The second thing is that the CDT has a lot of what I call as a low energy tail, which reduces the sensitivity of the instrument to lower energies that might be there, which are lost in that tail. So this is an example of a response function, how different detectors affect your sensitivity to any measurement. Okay, now let's take a look at this figure here. Can you look at the energy range here? You have energies around 10, 20, all the way up to say 130 or so, which is similar to what is Helios's range. Okay, so as you see here, the counts on the x-axis are matching for CDT and silicon up to around 15 kV or so. At higher energies, what happens is that the efficiency of the CDT detector is much more than that of the silicon. Okay, so in addition to understanding the response of a detector to an incident energy, you have to also know the efficiency. The efficiency tells you if I have 100 photons of a certain energy incident on a detector, how many of them are available to produce a signal? Simple as that. Okay, so you have to make what is called as an auxiliary response function, which tells you about the probability of detection of an X-ray energy. That's it. So efficiency is nothing but the probability of detection of an X-ray of some energy E. So to wind up, we have a source. We spoke and discussed a lot about the source of emission of X-rays in the solar rays, right? We know for an extent we can approximate it by something. We have thermal Maxwellian Röntgen, we have a non-thermal Röntgen, etc., etc. So we can approximate the source, and remember, we don't exactly know what the source is. We approximate it by what is called as a model. The model can be empirical in nature. Empirical in the sense you can understand the shape of the observation. For example, a power law can tell you if the spectrum is steep or if it is shallow, or an exponential can tell you what is the E folding or what is the 1 by E decay time of the spectrum. So empirical models tell you how this photon emission spectrum is shaped. Then you have physical models that are physics based. Say, for example, a thick target non-thermal Bremsstrahlung or a thermal Bremsstrahlung, which gives you the physical parameters of the plasma that is emitting that radiation. Okay, so then what you do, you take this model with a set of initial parameters. Say, for example, if you take a thermal Bremsstrahlung, you give it some initial value of temperature, you give it some initial value of plasma density, and for non-thermal Bremsstrahlung, you give it the initial value of electron index, spectral index. Then what you do is you convolve this model with the efficiency of the instrument, which is your auxiliary response function, and your response matrix. So I put dot here because it's the lowest energy and the highest energy, and in between you will have the corresponding response function of all the other energies. Okay. Then what you get is a model spectrum. This model spectrum has to be compared with your observation by doing non-linear least squared fits, fitting the data. Okay, that is what you're going to do for your project. So this red curve here is the best fit, taking the model, iterating it over a number of different parameters, and fitting it with the data until you get a minimum value of the goodness of the statistic. In this case, it is called the chi-square. And this is the formula where C of I is your observation, P of I is your model, and sigma of I is the error on your data. That gives you the best of it. So we generally go, I guess, around 0.8 to 1.5 or 2. We go in that range of value to say that the data are the best good fit. Okay, so to close this lecture, I'll show you. Abhilash has made this slide. So you have a flare which is plotted, I think, in 304 angstrom of AIA, and the corresponding data seen in the SOLEX, and the corresponding data seen in the CDT detector of Helios. Okay. So with this, I close, and any doubts and questions you have on this, we can sort of take it either after this series or after this talk. Thank you so much.
Thank you, Manju, for explaining how I saw the missions are different. So we have some time for questions, but yeah, I'll suggest one or two questions, then we should be able to end. Yeah.
And also we divide our energy so different and each energy weight.